Hi everyone, my name is Anthony Rebello and I'm going to be presenting this talk titled Can Applications Recover from fsync Failures? Co-authored by Yuvraj, Patel, Ramnatthan, Alagappan, Andrea Arpaci-Dusseau and Remzi Arpaci-Dusseau from the University of Wisconsin-Madison. We'll start with a little bit of background on how data reaches the disk, as fsync plays an important role here. Generally, applications don't interact with the disk directly. Instead, they use the file system through system calls such as open, read, and write. However, when they use this write system call, the file system doesn't really write to disk immediately. It buffers it in the page cache and marks those pages dirty. Once in a while, the file system will flush these dirty pages to disk. While this approach lets writes complete fast, the drawback is that your application can lose data for the period that it is in RAM. So if you want to force data to disk immediately instead of waiting, you can call fsync after the write, and this will ensure that all dirty pages for that file are synced to disk. By the way, I am going to be using the same representation for pages throughout the presentation. Clean pages will match the color of the disk, a blue color, and dirty pages a red color. So as you can guess, fsync is really important. The ability to force data to disk immediately allows applications to provide durability guarantees. In most cases, applications want to acknowledge a user's write or modification and guarantee that those changes will survive power failure or crash. And fsync helps you do that. And even if you are bypassing the page cache and using direct I/O, your data could be sitting in the volatile portion of the device. You still need to call fsync to issue a flush command to the device, which moves the data into the non-volatile region. And lastly, sometimes you want to force some data to disk before other data is written. This ordering can be enforced using fsync. If you're interested in this, you should check out prior work from our group, which decouples ordering from durability. So while fsync is important for durability, applications find it really difficult to get it right, even when fsync works correctly. Take for instance the case of creating and writing to a file. On some file systems, you can't just fsync the file itself. You will also have to fsync the directory to ensure that the entries persisted so you can access this file in the future. This example is one of taken from prior work, where the authors found several vulnerabilities when applications try to get durability right. Update protocols are tricky. And it just becomes tougher for applications when you think about the fact that fsync can fail. Sometimes fsync fails for simple reasons. For example, passing bad arguments or not enough space. And these are quite easy to handle and check for before interacting with the disk. But we are more concerned about the fsync failures that occur after a file system interacts with the disk. Because at this point, the file system has already modified its internal state while getting ready to write to disk. And disks can fail. Transient failures are common, and now cloud providers are offering disks that can be attached or removed over the network, so you are susceptible to network failures as well. So if the file system encounters failures at this point, it returns -1 and sets the error code to EIO. And because in-memory state has been modified, it might need to revert it. And these fsync failures are important. To quote Thomas Wandra from FOSDEM last year, about a year ago, the Postgres community discovered that fsync on Linux and some BSD systems may not work the way we always thought it did, with possibly disastrous consequences for data durability and consistency, which is something the Postgres community really values. They had been using fsync incorrectly for years. Specifically, they made some incorrect assumptions about the way file systems handle failures during fsync. So our work is about systematically understanding the fsync problem in two pieces of the storage stack. First, on file systems, we study how they react to failures during fsync. We do this for ext4, XFS, and Btrfs. And once we characterize these file systems based on their fsync failure reactions, we move to the next part. We look at 5 widely used applications and see how effective their strategies are when fsync fails. Postgres moved away from retrying and used a crash restart strategy. We wanted to see if other applications out there were trying out different strategies and figure out what's effective and what's not. So here's our results at a high level. All 3 file systems marked the dirty pages clean after fsync failure, and so retries were pretty much useless. And although they mark the page clean, they don't handle errors uniformly. ext4 and XFS keep the latest content in RAM, while Btrfs reverts it. And ext4 data mode reports errors later than the others. Lastly, the in-memory data structures are not entirely reverted. So in ext4 and XFS, the free space and block allocations remain unaltered, much like the page content, and you end up with blocks belonging to your file that don't have the data you wrote to it. With Btrfs, although reverted, the file descriptor points to an offset ahead of the file, so you end up with a hole for that skipped region. And coming to applications, it's easy to see why retries were ineffective, since dirty pages were marked clean. But it turns out crash restart isn't completely correct either. We notice these failures we call false failures, where an application informs the user that the operation has failed, but the state of the application is as if the operation succeeded. And these occur usually during the restart phase because recovery ends up reading the latest content of the log from the page cache. ext4's data mode reports errors later, and this is quite problematic. Applications require immediate notifications for their strategies to be effective. We see that most applications faced corruptions and all had cases of data loss. Btrfs did have the least number of data loss instances and false failures, and it seems pretty good for strategies that recover from a write-ahead log. But it's particularly bad for rollback strategies, and I'll be diving deeper into each of these in the talk. So with that, we have our introduction. For the rest of the talk, I'm going to go over the two parts, file systems first and then applications, and then conclude with a few points of what challenges we might face while going forward. To study file systems on an unmodified kernel, we decided to inject faults at the block layer. We did this by building a device mapper tool, dmloki, to intercept block requests. We wanted something that could fail things deterministically. You could configure dmloki to allow the first 5 writes to pass, fail the 6th and 7th, and then let everything succeed after that. And we simplified the operations we thought were common to most applications. The first is a single block update. Essentially, you're modifying a file in place. The content changes and maybe the timestamps, but your file doesn't shrink or grow. So we modify the middle page in a 3-page file. And this is pretty common, especially when updating entries in databases. The second is multi-block append, where you're growing a file by adding blocks to the end of the file. You typically see this in write-ahead logs. So let's dive into the results. We found that all 3 file systems mark the page clean. Taking the in-place modification as an example, when the write system call returns, the middle page is dirty. And we configured dmloki to fail the write to the disk, so when fsync is called, it fails, but the page isn't dirty anymore. And this isn't really a bug. There's been a lot of emails between the Postgres community and the file system developers regarding this. Turns out the main reason is the support for removable USB sticks. If a user pulls out a USB stick while there are dirty pages, keeping them dirty would cause a memory leak. And to the file system developers, there are way more users like that compared to Postgres installations. And you can see why retries are ineffective. If the page is marked clean, the next fsync won't do anything since there aren't any dirty pages to write out. And because there aren't any pages to write out, there are no errors. So the application will actually think that fsync succeeds, even though nothing was written. This was the crux of the Postgres issue, where they truncated the write-ahead log, thinking that fsync succeeded to persist their data. And while file systems have marking pages clean in common, they actually differ in what's contained in these pages. Using the same example as before, if you're modifying the middle block from B to X, the disk still contains B since fsync fails. But on ext4 and XFS, even though the page is clean, it contains the latest write X. Btrfs reverts back to the old content because of its copy on write approach. So you cannot depend on the page cache content after a failure. Also, ext4 data mode reports errors later than the other file systems. It does this because the fsync writes your data to the journal. At that point, it may succeed. But if it fails to write the data out of the journal to the actual block location, it just empties the journal and logs the error to syslog. If you happen to call fsync later, you'll get to know about it. But it might be too late at that point. We did notice that always following with a second fsync forces that data to be written out of the journal. So you can detect the problem early on. Moving on to in-memory state, we find that ext4 and XFS don't try to revert them. Although the fsync operation is stopped when they see a data block failure, the other metadata is left intact, just like the page content. We're going to walk through this with the append workload, where we initially just have a single 4KB file. The first thing to notice here is that there is a link that associates the offset array with a block on disk. This is like the INO table containing the links to the actual blocks. When you write B to the end of the file, there's a dirty page. And if the fsync fails, the page is marked clean and no metadata is written. But the link for that offset to the block is not reverted. It's not persisted yet though. But if you unmount the file system or wait for a while, it will be persisted. And now you have a link to a block, but not the content you wrote. We call these non-overwritten blocks. Also, if you proceed to write in fsync more data, that persists the link as well. And if an application tries to read these contents from disk, it's a corruption. On Btrfs, the entire state is reverted, but if you keep writing, it writes at the updated offset. So you end up with a hole in that region. Again, if an application reads that block, it will see zeros, which is also a corruption. So to summarize, we've seen dirty pages marked clean even after failure on all file systems. They don't handle errors in a standard way. The page content differs and ext4 data mode reports failures later than the others. And in-memory data structures are incorrect, leading to applications facing corruptions or data loss depending on whether the non-overwritten block is an in-place update or an append. And now we move on to applications. We study 5 widely used applications. 3 of them are embedded, 2 servers, and we have a mix of key-value stores and relational databases. Our goal here is to find out whether an application's strategies are effective when fsync fails. So we choose a simple workload that inserts or updates a single key-value pair. For relational databases, we use a 2-column table. And we fail the fsync, not by mocking it, but by actually causing fsync to fail for some underlying reason. And after that, we dump all key-value pairs if the application is still running. We do that even when it restarts. We also force page evictions and machine restarts and dump the key-value pairs. This gives us an idea of whether there is data loss, corruptions, or false failures, and when they occur. We built our own file system in user space called CuttleFS to help inject faults deterministically. We needed this because we didn't want to deal with failing specific blocks. dmloki was useful when the workload was simple, but applications are much more complex, and it's not possible to always get the same block allotted to a file. Using file names and offsets was easier. Also, we were able to simulate the different failure reactions from the file systems we studied earlier by using our own user space page cache. So marking pages clean, changing what content was served, and when fsync errors were reported were all in our control. This also made it easier for us to choose what pages were evicted and when. So to give you an overview of the results, we found false failures mainly in ext4's ordered mode and XFS. And this is mostly to do with recovery from the write-ahead log, which we'll get to shortly. Data loss and corruptions were mostly in ext4 data mode due to late error reporting. Redis has a lot of errors because they don't check the fsync return code. And Btrfs had minimal errors. We'll first go over false failures in ext4's ordered mode, and then data mode, and then Btrfs. We're not going to cover XFS as it's similar to ext4 ordered mode. So we know that the simple retry strategy fails, but crash restart was also not completely correct. The main issue here is that when restarting, you're reading from the page cache. We're going to look at Postgres as an example. So Postgres maintains tables as files on disk and also has a write-ahead log. And when it starts up, it loads the tables and replays any operations from the log. So here A changes from 0 to 1. And now when you update A to 2, Postgres first writes it to the log, dirtying the page. It then fsyncs the log before responding to the user because it has to survive power failures. And only after an fsync can you be guaranteed that it will be replayed. But say the fsync fails. So the transaction fails and Postgres crashes intentionally. The page is marked clean, but on ext4 and XFS, the content is still in the page cache. So when you restart, you're rebuilding incorrect state. The state represents the successful operation even though it had failed. We call these false failures. And false failures are bad. If you run queries and get a failure, users typically just retry it. No one checks if it passed because you told us it failed. These may not be a problem for idempotent operations like setting absolute values, but they are a problem when, say, decrementing. A retry here could cause a double decrement. We find these in every application except Redis. Redis always reports success because it never checks if fsync fails. There's also this false sense of durability with the ext4's data mode, that just because it writes data to the journal, you're safer than usual. But this isn't true. Finding out about errors later is actually more dangerous and causes data loss for every application we've studied. For example, say you're updating A's value to 2. So the page is dirty, and now you fsync. Fsync succeeds since ext4 puts it in the journal, so you report this success to the user. But when ext4 fails to move the data out of the journal, it just logs it in syslog. So it's not on disk and it's not in the journal, it's only in the page cache. If the machine restarts, you've lost your data. A's value is 1. And while this is just for the write-ahead log, it also happens during Postgres checkpoints. And this is just data loss, but we've documented cases of corruption for all the other applications as well. So it looks like the copy on write strategy where you revert on failure is working pretty well. We don't find too many failures on Btrfs. And because the page contents match the disk, it works well with the crash restart strategy when recovering from the write-ahead log. But it doesn't really work for SQLite and rollback mode. We're going to see why. So in SQLite, if you run a query that is going to modify a page, it first writes the original contents of the page to the rollback journal. That way you can always revert state if you abort the transaction. SQLite then proceeds to dirty the page in the main database with the updated value. And right before committing, it fsyncs the rollback first. It has to make sure that the rollback is safe before it can persist the main database changes. But if it fails here, it's relying on the fact that it can recover using the rollback. Unfortunately, on Btrfs, the rollback file has been reverted. So SQLite thinks there is nothing to revert and you keep the new state, a false failure. And this is just to prove that Btrfs isn't bulletproof, but it's worse on ext4 and XFS. We found that the same scenario caused corruptions because you might roll back from a non-overwritten block. So to summarize, simple strategies aren't effective, and you don't want to trust the page cache while recovering state. Most applications have issues with ext4's data mode, but doing a double fsync seems like a quick fix. And Btrfs's copy on write approach is promising, but you have to be careful when using a rollback strategy. So we've seen that applications still face errors after fsync failures. They don't handle them correctly, not entirely, but can they recover from them? Right now, you could if you wrote file system specific code, but we probably need to standardize file system behavior, especially when fsync fails. POSIX is really vague on that. I wanted to conclude with a few things to think about when trying to solve this problem. If you're looking at uniform behavior, FreeBSD redirties the pages at the VFS layer when it sees a failure. And there has been some discussion online about doing the same in Linux. Maybe using a flag when mounting to choose whether to redirty or keep the pages clean after a failure. But it isn't that simple because file systems like Btrfs revert the content before it goes back out to the VFS layer. So it may not be a simple fix. The second is whether we want applications to be aware of file system differences in an operating system. The major one is if you're on a Mac, you can't just fsync, you have to call ffullsync. But do we want applications to actually think about differences within an operating system? We also need a stronger contract once a file system promises that your data is on disk. ext4's data mode emptying the journal even when it fails to write the data block is not good enough. And lastly, applications do a lot of testing, but just ensure that you're testing the file system's error handling code paths too, because how you recover depends on the state of the system after the failure. If you go the block fault injection route, dmloki can help you. Or you can simulate all the post-failure characteristics using CuttleFS. To conclude, durability is important and fsync is essential. We still want to use the page cache. It has a lot of performance benefits and no one wants to re-implement their own cache. So fsync is a good way of forcing things to disk when you want to. Failures are inevitable though. I don't think it's wise to ever assume that disks or cloud-provided attached storage will be free of faults. And so failure handling code is necessary. But just remember that different file systems handle fsync failures differently. So if you're trying a specific technique, make sure you understand the characteristics of all the file systems you're supporting. And we've seen that applications handle fsync errors differently, but no single strategy works well on all file systems, at least not if you want the benefits of the page cache. We have a lot more results in the paper, and they describe the exact conditions that cause these failures and more. I hope you enjoy it. Thank you.